Okay, so today we're going to be learning about gases, and before we start learning about gases, let's first talk about something known as the kinetic theory of gases. Okay, this is something from O levels. Kinetic theory of gases. Okay, and we're going to talk about the ideal gas assumptions. The ideal gas assumptions, and I'll just talk about what we mean by an ideal gas. What do we mean by an ideal gas? Okay, we'll just talk about that now. These are this is what the kinetic theory of gases outlines, right? Gases are made up of tiny particles called molecules in a state of rapid random motion. So you can have diatomic molecules, for example, oxygen gas is a diatomic molecule. You can have monoatomic molecules, for example, argon is a monoatomic molecule. It's just a single atom that's a molecule. Okay, and these molecules are always in motion, state of random and rapid motion. The average kinetic energy is directly proportional to the temperature in Kelvin. In other words, the higher the temperature, the greater the kinetic energy. All collisions are perfectly elastic. In other words, when two gas particles collide with each other, right, there's no loss in kinetic energy and no loss in momentum, right? Elastic collisions. And collisions between the molecules and the walls of the container give rise to pressure. Now, the two most important assumptions that we make, are these two. Okay, you don't have to write these down. We're going to look at these later as well. But the two most important assumptions are this one. The first major assumption that we make is that the volume of the molecules is negligible compared to the volume of the gas. Okay, this is the first important ideal gas assumption. Okay. So, for example, let's look at a glass of water, right? So let's say that I have 1 mole of water, right? Now at room temperature and pressure, that 1 mole of water, right, it's liquid, right? And 1 mole has a mass of 18 grams. So this 1 mole of water occupies 18 centimeter cube. So that's around 18 milliliters. Okay, centimeter cube and milliliters are the same thing. So that's the volume that this 1 mole of water occupies. So you have a very, very small volume, 18 milliliters. Now on the other hand, let's take this big box over here, okay? And let's say that in this big box I have 1 mole of oxygen gas. 1 mole of oxygen gas at RTP. Okay? And this occupies a volume of how much? Any gas occupies a volume of how much? Remember, we made that assumption earlier in moles. We learned that occupies a volume of 24 decimeter cube. 24 decimeter cube, in other words, 24 liters. Now, if you think about this for a second, what we see is that 1 mole of water and 1 mole of oxygen gas, they both contain the same number of molecules. They both have 6.02 times 10 to the power of 23 molecules. There's same number of molecules here that you have over here. But this occupies more than 1,000 times the volume that the liquid occupies, that water occupies. This occupies more than 1,000 times the volume. Same number of particles occupy more than 1,000 times the volume because it's in the gaseous state. So over here, we have these molecules that are very, very far spread apart. So now, can I say that the volume of the molecules themselves, if I look at these dots over here, these are the different molecules that I have. Can I say that the volume of the molecules, if you add up the total volume of the molecules, it's very, very, very tiny compared to the actual space that it occupies? And therefore, we can say that the volume of the molecules themselves, the actual molecules, the physical molecules themselves, is much, much smaller than the overall volume that the molecules occupy. So that's the first important assumption. And you should write this one down. Okay. बेसिकली हम लोग ये बोल रहे हैं कि मॉलिक्यूल्स खुद ही इतनी छोटी हैं कि मॉलिक्यूल्स की जो अपनी खुद की वॉल्यूम है ज़ीरो कंपेयर टू द एक्चुअल वॉल्यूम दैट द मॉलिक्यूल्स ऑक्यूपाई. So for example, like the oxygen की जो molecules हैं, they're occupying, this entire 24 liters, but they can actually fit into such a tiny little space. So can I assume that the volume जो molecules उनकी खुद की जो volume है उन particles की वो zero है या negligible है compared to the actual volume that the gas occupies? So this is the first key assumption again, that the volume of the molecules themselves we can assume it to be zero, even though it's not actually zero. That's why it's an assumption. It's not actually zero, but it's so small that we can assume it to be zero. So that's the first important ideal gas assumption. The next key assumption that we have, is this one. And again, this is one you should write it down. And the assumption is that the attractive forces or the intermolecular forces between gas particles are negligible. In other words, there are zero intermolecular forces or zero attractive forces between gas molecules. Now, again, if you look at the sample of oxygen, you have tiny, tiny little molecules that are so spread apart, that they're not really attracting each other. Now, we know again that intermolecular forces do actually exist between molecules, but we're assuming that there are no intermolecular forces in gases because these gases are so far spread apart. Okay, so we can say that attractive forces or intermolecular forces between particles are negligible or very much equal to zero. So we can assume zero intermolecular forces because these gas particles are so far apart, they don't attract each other. Again, this is not entirely true. They do actually have attractive forces between them, but we can assume that they don't exist in gases. So these are your two key ideal gas assumptions. Over here. The first assumption that we had over here was that the volume of the molecules is negligible compared to the volume of the gas or the container. Okay, compared to the volume of the gas or the container that it occupies. Okay, and then the second key assumption over here is that the attractive forces or the intermolecular forces between these particles is negligible. The third key assumption over here is that the collisions between gases are perfectly elastic. Even again, this is not entirely true. You can have inelastic collisions between gases as well, but we are assuming that all the collisions will be perfectly elastic. Okay, we can assume that all the collisions will be perfectly elastic over here. Okay, now a gas that behaves this way, in other words, if these assumptions were true for a gas, we call that gas an ideal gas. That's why these are called the ideal gas assumptions. We're saying that if a gas were to behave these assumptions, we would call it an ideal gas. Okay, so an ideal gas is sort of a theoretical gas. It's not an actual gas. It's not a real gas. But we're assuming that gases behave this way. And if these assumptions are true, we're going to say that, okay, if we have a gas that behaves this way, we're going to call that an ideal gas. So if a gas was to behave this way, we would say that the gas is behaving ideally. If a gas is behaving this way, we would say that the gas is behaving ideally. Okay? And that brings us to our next point, which is we have the ideal gas laws. So the ideal gas laws, okay, they apply to ideal gases, obviously, right? They don't apply to actual gases, but we assume in our calculations, we're going to assume that real gases are behaving as ideal gases. In other words, if a gas behaves ideally, okay, these laws are true. Okay, the first law that we have is Boyle's law. Okay, you don't need to know the names of the laws. That's part of physics. But the first law that we have is Boyle's law. And what does Boyle's law say? Well, now, Boyle's law over here says that the volume of a gas is inversely proportional to the pressure. Inversely proportional to the pressure. And if we had to write this down as a relationship, the pressure is inversely, or rather the volume that the gas occupies is inversely proportional to the pressure. So we can say that the volume is equal to some constant divided by the pressure. So what we can say over here is that the product of pressure and volume is a constant. The product of pressure and volume is a constant. So let's look at an example over here. Okay, let's say that I have a container over here. Okay, and what I'm doing over here is I'm applying a certain amount of pressure. I'm applying a certain amount of pressure. Okay, applying a certain amount of pressure. Let's call that P1. And then when I increase the pressure, let's call that P2. Okay, and let's say that that pressure over here is 2 times the initial pressure. So initially I was applying a pressure P1, then I increased the pressure, and what I've done over here is that I've doubled the pressure. So what do you think happens to the volume of the gas? Let's say that the volume over here was V1. Okay, what do you think happens to the volume of the gas if it's inversely proportional to the pressure? If I double the pressure, what happens to the volume? It becomes half, right? It becomes half the initial volume. Now, this is important. This is important because if you think about it, if you go back to the ideal gas assumptions, we're assuming that there's no intermolecular forces. So when I actually compress the gas, I'm assuming that when they get closer to each other, it's entirely because of the increase in pressure and not because of any intermolecular forces that are present. If those assumptions weren't true, right, then this law wouldn't be true. This law only applies if no intermolecular forces are present and if we're assuming that the volume of the particles themselves is negligible. So over here, what we see over here is that, okay, assuming that there's no intermolecular forces and assuming that the volume of the particles themselves is negligible, okay, we can say that the pressure is inversely proportional to the volume. So if I double the pressure, the volume will become half as much. And that gives us a very interesting relationship over here. That gives us the relationship P1V1 is equal to P2V2, right? And we can prove that. We know that if I've doubled the pressure, right, we know over here that if I've doubled the pressure, P2 is simply 2 times P1, and you know that what the volume is actually halved. So V2 is actually half times V1 over here. So we notice over here that we get the same thing, P1 V1. So this is a very important relationship that I'm sure you guys are familiar with, and that is that initially we had a certain pressure P and a certain volume V, okay, and now we have a new pressure P2 and a certain volume V2. And the product of the pressure and the volume will always remain a constant, assuming that the gas behaves ideally. And obviously over here, we're making sure that we have the same number of moles of gas, right? And we have the same temperature. So the number of moles and the temperature are obviously kept constant in both of these cases. So again, this relationship P1V1 equals to P2V2 applies when we're making sure that the number of moles and the temperature are kept constant. So all other factors are kept constant over here, okay? And we can see these relationships graphically as well. Okay, what we have here is we have that the pressure is inversely proportional to the volume, right? The pressure is inversely proportional to the volume. So as I increase the pressure, the volume decreases. Okay, so this is the graph of volume against pressure. Again, whereas this graph is true if we've kept the number of moles and the temperature constant. So those aren't affecting the volume in any way. Just the pressure is affecting the volume. So if I increase the pressure, the volume decreases. And since they're inversely proportional, this is the graph of volume against 1 over P. Okay, so the inverse of the pressure, right? Volume is directly proportional to 1 over P. Volume is directly proportional to 1 over P. So that's a straight line, and inversely proportional to the pressure itself. So that's the decreasing graph over here. This is the curve of sort of like 1 over X, right? If you guys are familiar with that from math, or this is the graph for Y is equal to X. So this actually covers Boyle's law over here. That's the first ideal gas law that we're learning about. Again, you don't need to know the name of the law, but you should know what the law states, and that is that the volume of a gas is inversely proportional to the pressure. The next law that we have over here is Charles' law. So Charles' law says that the volume of a gas is directly proportional proportional to the temperature, to the absolute temperature, okay? To the absolute temperature. So that will be in Kelvin, okay? In Kelvin. So the units for that will be Kelvin. So in other words, we can say that the volume that the gas occupies is directly proportional to the temperature, which implies that the volume is some constant times the temperature. So we can say over here that the ratio between volume and temperature is a constant. The ratio between volume and temperature is a constant. Again, over here, we're assuming that we're only varying the temperature. We're only varying the temperature, okay? And we're keeping what? Pressure, and again, number of moles are kept constant. So we have the same number of moles of gas at the same pressure, but now we're only varying the temperature. So again, let's look at an example here. Let's say that here in both cases, in both containers, I'm applying the same pressure. So I've kept the pressure constant, okay? And what I've done is, over here, I have a temperature of, let's say, 200 Kelvin, and here I have a temperature of 400 Kelvin, just as an example, okay? So now, if I've doubled the temperature, what do you think happens to the volume? If I say, okay, this is volume is V1, what do you think happens to the volume V2? If I've doubled the temperature, then I will double the volume. If I've doubled the temperature, I've doubled the volume. Again, note that this is only true if the ideal gas assumptions are true. We're assuming that gases are behaving ideally, because we're saying, acha, jaisi temperature badega, the molecules will move further apart based on that temperature. We're assuming there's no intermolecular forces. Those have no effect. Just kinetic energy particles ki बढ़ जाएगी as I increase the temperature. They'll collide more vigorously, and the gas is going to expand. Okay. So what I can say over here is, since the ratio between the volume and the temperature is a constant, if I say T1 is 200 Kelvin and T2 is 400 Kelvin, right? I can say that V1 over T1 is equal to V2 over T2. And we can verify this over here. What I've done is, since I've doubled the volume, I've also doubled the temperature, so the ratio between the two will remain the same. Okay, so this is another important relationship that we have between volume and temperature. Okay, again, we're keeping the pressure constant, and we have the same number of moles of gas in both containers. Okay, and the relationship graphically can be viewed as the following. The relationship can be viewed graphically as well. We can see over here that the volume and the temperature are directly proportional. As I increase the temperature, the volume increases by the same factor. Now the next law that we have over here is Avogadro's law. The next law that we have is Avogadro's law. Again, you don't need to know the names of these laws, but you should know what these laws state, okay? Now, Avogadro's law says that the volume occupied by a gas is directly proportional to the number of moles of gas, in other words, the number of molecules, right, of gas. Okay, since the number of molecules is just a constant times the number of moles, Avogadro's number, right? So we have the number of moles of gas is directly proportional to the volume. And what that means over here is that, again, this is only true if we make sure that temperature and pressure are constant, right? So if you have a constant temperature and a constant pressure, if I double the number of moles of gas, I'll have double the volume. So for example, at room temperature and pressure, we've said that 1 mole of gas will occupy 24 decimeter cubes, 2 moles of gas will occupy 48 decimeter cube, and so on, right? So here we can say that the volume is directly proportional to the number of moles of a gas, and therefore we can say that the volume is equal to some constant times the number of moles of gas, right? And therefore we can say that the ratio between volume and the number of moles of gas is a constant. So now what we've seen so far is that when pressure is inversely proportional to the volume, right? That's Boyle's law. Again, you don't need to know that name, but we know that pressure is inversely proportional to volume. So the product of pressure and volume is a constant, right? We've also learned that volume and temperature are directly proportional. So the ratio between volume and temperature is a constant. And we've also learned that the volume of a gas is directly proportional to the number of moles. In other words, the ratio between the volume and the number of moles N is also a constant. So can I say over here that this entire expression is a constant? The ratio, the product of product and volume is a constant, pressure and volume is a constant. The ratio of volume and temperature is a constant. And the ratio of volume and the number of moles is a constant. So I can say that this is also a constant. And this is known as, this constant over here is known as R. Okay? This is known as the ideal gas constant. This is known as the ideal gas constant. And the letter we use for it is R. The ideal gas constant. Okay? And the value of this constant is 8.31 joules per mole per Kelvin. Okay? And if we rearrange this expression, what we get is we get the following equation. PV is equal to nRT. PV is equal to nRT. And this equation here, okay, this equation over here is known as the ideal gas equation. Okay, over here, P is the pressure. Okay, in pascals, we'll always use SI units in this expression. So P is the pressure in pascals, volume, V is the volume in meter cube. Okay, for the ideal gas equation, always use SI units. Okay, N is the number of moles, right? Number of moles key units are just moles, obviously. R is the ideal gas constant. So that's 8.31 joules per mole per Kelvin. Okay, and T is the temperature in Kelvin. This is joules over here. Again, this equation, okay, should only, whenever you use this equation, always use SI units in this expression, okay? And this equation is only true if those assumptions are true. In other words, if a gas behaves ideally, this equation will apply. So for our calculations, we're going to assume that gases behave ideally, okay? For our calculations, we're going to assume that gases are behaving ideally. So here we have an example of a question, okay? The question says the volume of a sample of ammonia is measured at a temperature of 60 degrees Celsius and a pressure of 103 kilopascals. The volume measured is 5.37 times 10 to the power of -3 meter cube. What is the mass of the sample of ammonia given to two significant figures? Right. First of all, we have the ideal gas equation. We want to find the mass of ammonia. But what can we find first over here? What can we find first? We can calculate the moles of ammonia. Good. So the first thing we're going to do is we're going to calculate the moles of ammonia over here. Now the pressure is 103 kilopascals. So that would be 103,000 pascals. Okay, 103,000 pascals. The volume is already given in meter cube. It's 5.37 times 10 to the power of -3. Right? 5.37 times 10 to the power of -3. And this is equal to the number of moles, which we have to calculate, times the ideal gas constant, that's R, and the temperature is given to us as 60 degrees Celsius. So we're going to take the temperature in Kelvin. So that will be 273 plus 60. Okay, remember the temperature in Kelvin is temperature in Celsius plus 273. Okay. So if you do this calculation, you should get number of moles is equal to 0.200 moles. Right? So then, if we have to find the mass of ammonia, we can say that the number of moles is equal to the mass divided by the molar mass, which implies that for ammonia, right, the molar mass is 14 plus 3. or the molecular mass, which is 17. Okay. So what we get over here is that the mass is equal to the number of moles times the molar mass. So then what is the mass of ammonia over here? The mass is 3.4 grams. So the answer over here is D. The next question that we have here is this one. Okay, the next question that we have is this one over here. The question says, when an evacuated glass tube of volume 200 centimeter cube is filled with a gas at 300 Kelvin and 101 kilopascals, the mass of the tube increases by 1.06 grams. What is the identity of the gas? So again, what's the first thing you would do here? The first thing you would do is you would use the ideal gas equation. And what are we going to try to calculate? The number of moles. We want to find the mass, and the number of moles is simply the mass over the molar mass. So once we find the molar mass of the gas, right, we have the mass given to us. We have to find the number of moles so we can find the molar mass and determine the identity. Okay. Now, the pressure is given to us as 101,000 pascals, 101 kilopascals. The volume is given to us in centimeter cube. Does anyone know the conversion between meter cube and centimeter cube? Right, 1 meter cube is 10 to the power of 6 centimeter cube. Right? Does everyone know this conversion from physics? Okay. So what we have over here is, if we have 200 centimeter cube, we have 200 divided by 10 to the power of 6 meter cube. Okay, that's the volume in meter cube. And this is equal to the number of moles times the ideal gas constant times the temperature in Kelvin. Okay, which is 300 Kelvin. They've given us the temperature in Kelvin here. So we have 300 Kelvin. So what is the number of moles over here? So the number of moles that we get over here is 0.00810 moles. So now we can find the molar mass of the gas to determine the identity. So we know that the number of moles is 0.00810, and that is equal to the mass, which is 1.06 grams divided by the molar mass, or the molecular mass over here. So that implies that the molar mass is 1.06 divided by 0.00810. So this comes out to 130.9 grams per mole. Okay. Now in the periodic table, xenon has a mass of 131.3. That's the relative atomic mass of xenon. So this is actually very close to the mass of xenon over here. So we can say that the identity of the gas over here is xenon. So the answer is D. To 3 significant figures, our answer is 131. So that these two match over here. Okay. Next question that we have here is this one. The question says, two glass vessels M and N are connected by a closed valve. M contains helium at 20 degrees Celsius at a pressure of 1 into 10 to the power of 5 pascals. N has been evacuated and has 3 times the volume of M. Okay, so N is empty, okay, whereas M contains helium, and the volume over here, if we call this V, right, the volume over here is 3 times V. Okay. In an experiment, the valve is opened and the temperature of the whole apparatus is raised to 100 degrees Celsius. What is the final pressure in the system? Now, can I say over here, yes, you can solve, but there's an easier way of doing it. Can I say that before I open the valve and after I open the valve, the number of moles of gas are the same throughout? Can I say that the number of moles of gas are the same throughout? Right? So the relationship that we have over here is, I should have mentioned this earlier, but the relationship that we have over here is P1 V1 over T1 is equal to P2 V2 over T2. Agreed? Because the product of pressure and volume is a constant, and the ratio between volume and temperature is a constant. Can we say that these two will remain the same? Since over here, the number of moles is simply PV over number of moles is simply PV over T, right? RT. Agreed? So far? Right? Since PV is equal to NRT. So can I say that that if we have R on both sides, R will just cancel out, that the product of the pressure and the volume and the ratio between this and the temperature is the same. P1 V1 over T1 is equal to P2 V2 over T2. Right? If you rearrange this expression, we can see that NR is equal to PV over T. So PV over T is a constant. Since I have the same number of moles, yeah, number of moles तो उतने ही है ना. इसमें जितनी गैस थी हमने बस खोल दिया और अब वो गैस दोनों जगह चली गई. लेकिन मैं ये कह सकता हूँ कि आपका जो नंबर ऑफ मोल्स ऑफ हीलियम था वो तो चेंज नहीं हुआ ना. उतना ही हीलियम शुरू में था जितने आखिर में था. बस नाउ इट्स ऑक्यूपाइंग अ लार्जर वॉल्यूम. अग्रीड? Right? So you have the same number of moles of helium, and we can see that PV over T is a constant. So now what we have over here is we have P1, which is 10 to the power of 5 pascals. That's the initial pressure. Okay. We have the initial volume, let's call that V, and we have the initial temperature, which was 293 Kelvin, right? 293 Kelvin. Since we have 20 degrees Celsius as the initial temperature. And the final pressure is what we have to find. That's P2. Okay. What's the final volume in terms of V that the gas is occupying? Initially, it was occupying a volume of just V. If I open the valve, then what's the volume that it's occupying? 3V plus V. So that would be 4V. And what's the final temperature? 100 degrees Celsius. So that would be 273 plus 100, which is 373 Kelvin. So on both sides, if you divide V on both sides, the V's cancel out. So I can find P2 over here. This implies that P2 is equal to, right, we don't need to write Kelvin over here. P2 is equal to 373 times 10 to the power of 5 divided by 293 times 4. And this value should come out to 3.18 into 10 to the power of 4 pascals. So the answer over here is A. Okay. So this relationship P1 V1 over T1 is equal to P2 V2 over T2 can apply. This applies when the number of moles remain constant. Since the number of moles is constant, right, and obviously R is a constant, we know that the product of this and R is also a constant. So the PV over T is a constant, and if PV over T is a constant, then that means that P1 V1 over T1 is equal to P2 V2 over T2. Again, we're only going to use SI units for these calculations. Okay, so we're going to add 273 degrees Celsius to find Kelvin. Okay. One last thing I want to mention is sometimes if they give you the pressure in atmospheres, okay, 1 atmosphere, 1 atm, that standard conditions is 1.01 times 10 to the power of 5 pascals. Okay. Actually, it's exactly 101,325 pascals. Okay. But the 3 significant figures is this. Okay. So we just use 101,000 pascals as 1 atm. If they give you 1 atm pressure or standard conditions, then that means 25 degrees Celsius and 1 atmosphere pressure, which is this value here. All right. This is the next question that we have. The general gas equation can be used to calculate the MR value of a gas. For a sample of a gas of mass m grams, which expression will give the value of the MR? Now we want to find the MR, so we know that the ideal gas equation relates the number of moles, the temperature, the pressure, and the volume, right? And we have the ideal gas constant. So I can say over here that the number of moles is equal to PV over RT. And I know the number of moles is simply the mass divided by the MR. And this is equal to PV over RT, right? So if I multiply RT over there on both sides, right, and I divide PV on both sides and I multiply MR on that side, basically I rearrange this entire expression. I get M is equal to MRT over PV. That's the MR over here. So the answer over here is C. Now, the next law that we have, okay, the last law that we have over here is Dalton's law, of partial pressures. And this will be extremely useful. This will be extremely useful when we're studying equilibria, okay? So I want you guys to really understand this law over here, Dalton's law of partial pressures. Now, let's say that I have a room or I have a box, okay? And I say that, okay, in this box, okay, I have a total pressure of, let's say, 1000 pascals, okay? Or 100,000 pascals, just for simplicity, okay? And let's say that this box is filled with air, okay, it's filled with air. And I say that, you know what, 80% of it is nitrogen gas and 20% is oxygen gas, okay? Again, we know that the exact values are slightly different, but just for the sake of ease or assumption, we're just saying, okay, air is 80% nitrogen, 20% oxygen to make our calculations easier. What is the pressure due to nitrogen gas? What is the pressure due to nitrogen gas over here? The pressure due to nitrogen gas will be 80%, of the 100,000. So can I say that the pressure due to nitrogen gas would be 80,000 pascals? Okay. And can I say that the pressure due to oxygen gas will be 20%, which is 20,000 pascals. Okay. So what does Dalton's law say over here? What does Dalton's law say over here? Dalton's law says that the total pressure is equal to the sum of the individual pressures of all the gases in the container. Okay, so this over here we say is the partial pressure. This can be called the partial pressure of nitrogen gas, and this can be called the partial pressure of oxygen gas. Okay, and Dalton's law kya keh raha hai? It's saying that the total pressure, okay, Dalton's law says that the again, you don't need to know the name of the law, but you should know that the total pressure is equal to the sum of the partial pressures. Equal to the sum of the partial pressures. So in the next example, we can say, okay, we have a container. Okay, we have a container in which I have 0.5 moles of oxygen gas. Let's say that I have 2 moles of nitrogen gas, and let's say that I have 2 moles of methane gas. Okay, so these are my total number of moles. And what I'm saying over here is that my total pressure in this container, is, let's say, 100,000 pascals. Okay. Now, the question over here is what is the partial pressure of nitrogen, what is the partial pressure of oxygen, and what is the partial pressure of methane? That's my question. Now, if we want to find the partial pressure of any gas, we can say that it is X times the total pressure. And X over here represents the mole fraction. It represents the mole fraction. Okay. So the partial pressure is equal to the mole fraction times the total pressure. Partial pressure of any particular gas is equal to the mole fraction times the total pressure. Okay. Now what that means over here is what is the mole fraction? Okay. Mole fraction of a gas. The mole fraction of a gas is equal to the number of moles of the gas divided by the total number of moles of gas present. Okay, divided by the total number of moles of gas present. So if you want to find, let's say, the partial pressure of nitrogen, right? The mole fraction of nitrogen would be what? The mole fraction of nitrogen over here would be 2 2 divided by 4.5, right? That would be 2 over 4.5, which is 4 over 9, or if you want to write this as a decimal, it would be 0.444, right? And then, so what's the partial pressure of nitrogen gas? The partial pressure of nitrogen gas would be the mole fraction times the total pressure, which would be what? 100,000 pascals over here. So that would come out to 44,444, right? Because this is a repeating decimal, 0.44444, right? I'm just using my calculator, carrying on the value. So that's the partial pressure of nitrogen, okay? Since we have the same number of methane, right? Methane ka bhi partial pressure kya hoga? Methane ka bhi partial pressure will be 44,444 pascals, because I have the same number of moles of methane. So the mole fraction of methane would be the same, and therefore the partial pressure of methane would be the same. The idea here is this, that jitne zyada moles of gas hote hain, right? The pressure due to a gas is directly proportional to the number of moles, because it's directly proportional to the number of particles. So jitne zyada particles honge, utna zyada pressure hoga. So partial pressure, we can clearly see over here that the partial pressure due to nitrogen will be 4 times the partial pressure due to oxygen. The partial pressure due to methane will also be the 4 times the partial pressure due to oxygen. And over here we can say that, now if I want to find the partial pressure of oxygen, what can I do? There's 2 things I can do. Either I can take the mole fraction, which would be 0.5 over 4.5, and multiply it by the total pressure, right? That's mole fraction times the total pressure, number of moles of oxygen divided by total moles of gas. Or I can use Dalton's law. I know that the total pressure is the partial pressure due to oxygen plus the partial pressure due to methane plus the partial pressure due to nitrogen. Okay? So therefore over here, that I can also subtract the partial pressures due to nitrogen and methane to find the partial pressure of oxygen over here. So I can say that if I do 100,000 minus 44,444 minus 44,444, what does this come out to for oxygen? 11,1111 pascals. Okay, and you can calculate it either using the mole fraction, or we can just subtract. We can subtract it from the total pressure. The sum of all the individual pressures due to all the gases will be the total pressure. So iska jo pressure hoga, it will be proportional to how many moles you have of it. Iska bhi proportional hoga, So each of them is exerting a certain amount of pressure, and the sum of each of these individual partial pressures is the total pressure, since these are the only 3 gases that are present in the container. Okay. If you guys remember over here from O-level theory, right, that the pressure due to a gas, do you guys remember this? So for example, let's say that I have a balloon. Okay, right? And there are random gas particles moving around. Now, when these particles collide with the walls of the container, what does that give rise to? Collision between particles and the walls of the container. The walls of the container give rise to pressure. Right? Does everyone remember this? Since the gas particles are colliding with the walls of the container, they're exerting a force on the walls of the container, and that force per unit area is the pressure. And if I increase the number of gas particles, in other words, if I take a balloon, okay, and I inflate it with more gas, I put in more gas over here, what happens to the pressure inside the balloon? If I increase the number of moles of gas, what's happening to the pressure inside the balloon? If I'm inflating a balloon, the pressure is increasing. Pressure increases as the number of moles of gas increases. Okay, so that's the fundamental idea that we're applying over here. That's the fundamental idea that we're applying over here. That the total pressure will be directly proportional to the number of moles. Okay, and if I keep on, जिसके ज़्यादा moles होंगे वो gas ज़्यादा pressure exert कर रही होगी. Okay, जिसके ज़्यादा moles होंगे वो gas ज़्यादा pressure exert करेगी over here. Okay, so that's the fundamental idea over here. Okay, that collision between particles and the walls of the container give rise to pressure, and the greater the number of particles and the greater number of moles, right, the greater the pressure due to the gas. So if you have multiple gases, जिसके ज़्यादा moles होंगे वो ज़्यादा pressure exert करेगी, जिसके कम moles होंगे वो कम pressure exert करेगी, right? क्योंकि जितने ज़्यादा moles होंगे उतने ज़्यादा collisions उस gas की वजह से होंगे. Okay. The last thing I want to mention is this. Now, there's a bit of uncertainty around this last part, okay, because your Cambridge syllabus is a bit vague about it. A lot of people think that's been removed from the syllabus, but I'll quickly mention this, okay, since it's not that challenging a concept, okay. If you think about the ideal gas assumptions, we said that for ideal gases, right, in simple terms, you've already written these assumptions down. Right? There are no intermolecular forces present. Right? And we also said that the volume of the molecules themselves, of the particles, okay, is negligible. Okay, or we say that the particles occupy zero volume relative to the volume that the whole gas occupies, or the volume of the container, because a gas occupies the volume of the container. Now, my question is, at what conditions do you think these... now, if, for example, we were looking at real gases, right? Under what conditions do you think real gases behave most ideally? The conditions that you can vary over here are temperature and pressure. So, first let's think about temperature. When can we say that the intermolecular forces are very, 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 very weak? When temperature is high or low? Right? At higher temperatures, right? Because the higher the temperature, the higher the volume the gas is occupying, the further apart the particles, right? And at what temperature and if you think about pressure, do you think they behave most ideally at low pressures or high pressures? So if a real gas has to follow these assumptions, what do we want to do to the pressure? Right? If you want the gases, we want the volume of the container. So over here, let's think of it this way. We have over here a container, okay, and we have a certain amount of pressure, right? And what we're saying is that the volume of these particles is negligible compared to the volume of the container. And we're saying that no intermolecular forces are present because these are far away. Now, real gases mein, this is not true. Real gases mein kya hota hai? That intermolecular forces are present and the volume of the particles is not necessarily negligible. Now, if I had a very high pressure, let's say, if I had a very high pressure over here, okay, so I've increased the pressure significantly. Over here, okay. Now, can I say that the volume of the particles is negligible compared to the volume of the container? Relatively speaking. Now, can I say that the volume of the particles is negligible? At a low pressure, we can see that the particles themselves are very, very tiny compared to the space that they're occupying. But what about a high pressure? At high pressures, we see that the overall volume of the container is not significantly larger than the volume of the molecules themselves. So, we can say that real gases behave most ideally at higher temperature and lower pressures. Okay. If I decrease the temperature on the other hand, and I increase the pressure, okay, then the ideal gas laws don't hold true. Because at lower temperatures and higher pressures, right, the gas particles are much closer together. And when they're much closer together, what that means over here is that there's more intermolecular forces present. So that assumption is no longer true. And we also know that the volume of the container is much smaller. So now we can't say that the volume of the particles is negligible. पहले वॉल्यूम बहुत ज़्यादा थी पूरे कंटेनर की, तो हम कह सकते थे कि गैस पार्टिकल्स इतने छोटे हैं कि हम अस्यूम करते हैं कि उनकी साइज़ ज़ीरो है. बट नाउ वॉल्यूम कंटेनर की इतनी छोटी हो गई है कि हम ये नहीं कह सकते कि गैस पार्टिकल्स की जो साइज़ है वो ज़ीरो है कंपेयर टू द साइज ऑफ द कंटेनर. ओके, so they behave most ideally at higher temperatures and lower pressures, and they behave least ideally at, or they don't behave ideally at, lower temperatures and higher pressures. Okay, so at lower temperatures and higher pressures, they do not behave ideally. Okay, and the last thing that I want to mention here, over here is the comparison of real gases and ideal gases. Okay, so here's an example. Now, ideally speaking, what do we see here? Ideally speaking, we know that the product of pressure and volume is a constant for an ideal gas. Okay, but let's say that, so for example, if I increase the pressure by a factor of 2, right? If I increase the pressure by a factor of 2, then the volume will decrease by a factor of 2. So ideally speaking, the product of pressure and volume is a constant. On the other hand, however, when I actually increase the pressure of the molecule, right, of the containers, or exert a greater pressure on the gas, what happens is that because intermolecular forces are present, right, the gases get closer than expected. So they're not just getting closer. So for example, right, if I double the pressure for a real gas, what will happen is that the volume will be divided by some factor greater than 2. Why? Because intermolecular forces are present. So the product of pressure and volume will actually not be a constant. Pressure double कर रहे हो लेकिन volume let's say 1/3 हो रही है या 1/4 हो रही है. So the product is actually decreasing initially because molecules are getting closer than expected. Okay, and the stronger the intermolecular forces, so for example ammonia में hydrogen bonding है, the stronger the intermolecular forces, the closer they'll get than expected. Okay, if I keep compressing the gas, what happens is, because the molecules actually occupy space, I can't compress the physical molecule itself. मैंने उनके बीच में जगह इतनी कम कर दी है कि वो मज़ीद नहीं दब सकती. तो मैं प्रेशर बढ़ाए जा रहा हूँ लेकिन वॉल्यूम कम नहीं हो रही. तो इवेंचुअली क्या होगा? मैं प्रेशर बढ़ाए जा रहा हूँ लेकिन वॉल्यूम कम नहीं होगी. Okay, so what will happen is that eventually the product of pressure and volume will increase. Okay, so eventually the product of pressure and volume will increase. Okay, now helium is the most ideal gas. Okay, it's the most ideal gas amongst the real gases. The reason why is because it's the smallest, it has the weakest intermolecular forces, okay, and it has the smallest volume. Remember, go back to the ideal gas assumptions for a second. Okay, right? The assumption here is that there are no intermolecular forces. Now, helium में सिर्फ 2 electron होते हैं. So it has very weak intermolecular forces. And we say volume of particles is negligible, यानी कि particles themselves, or the atoms themselves, or the molecules are tiny. And helium is the smallest atom. So it's the most ideal gas because it has the weakest intermolecular forces and the smallest particle size. Okay. The next most ideal gas that we have is hydrogen. Hydrogen may be negligible intermolecular forces होती हैं, so they don't really get closer to each other. Okay, so hydrogen and helium are the most ideal gases. Helium being the most ideal gas because it's also the smallest. Okay, whereas the stronger the intermolecular forces get, The stronger the intermolecular forces get, the more you see a deviation from ideal behavior. Okay. So this deviation here is known as negative deviation. Negative deviation क्या होती है? Okay. You can write this down in your from your notes later. Okay. But I'll just mention it. Negative deviation होती है when you have intermolecular forces present, the particles get closer than expected. And this increase over here is positive deviation. Positive deviation क्या होती है? That even though I'm constantly increasing the pressure, अब मज़ीद volume कम नहीं हो रही, because वो particles जो हैं वो मज़ीद आप compress नहीं कर सकते. आपने उनके बीच में space कम कर दिया, आप उनको मज़ीद कम नहीं कर पा रहे. तो आप pressure बढ़ाए जा रहे हो, लेकिन volume कम नहीं हो रही. Okay? आप pressure बढ़ाए जा रहे हो, लेकिन volume कम नहीं हो रही. Okay? So this is for negative deviation, and then for positive, you keep increasing the pressure, but the volume doesn't change. You keep increasing the pressure, but the volume no longer changes. So the product between pressure and volume increases.